So the first talk after Guido, the invited talk for this session is by Leuschel. He's going to tell us about the B language and its applications in real life problems and so on. So go ahead, Mihail.
Okay, thank you. I'll try to share the screen. Oh, desktop. Desktop 2. Share. Oh, no, I have to. Zoom. Okay. I have to quit and reopen. I'll do it very quickly. Sorry.
Michael has done really impressive work. He's the recipient of the first Prolog Prize given to the applications for 50 years of Prolog. And he has this system, if you apparently, I don't know all of them, the Paris trains or Toronto trains, those systems are validated or some, you now maybe even running some controls using his system.
Yes.
And the B programming language, to me, almost like Python, except of course, P is the specification language is very mathematical.
Mm-hmm.
Thank you for the Pavel for the long, interesting question, and thanks, Peter, for the answers. There are just so many questions, and people ask very involved questions. I had a lot of those I didn't ask.
Yeah. Okay, so Mihail, let's share the screen. Go ahead, Mihail. We cannot hear you if you're speaking.
It's working.
We can see your screen, but you're muted, Mihail.
You're still muted.
Yeah.
Your screen's fine.
Okay, sorry. Yeah, the unmute button was not visible while sharing the screen.
Yeah, sometimes so crazy when the Zoom share screen, everything disappeared.
All right,
Okay,
now
so,
you have both working. Go ahead, Mihail.
Okay, so sorry for the delay. Okay, so I'm glad I have some time now, a little bit less, to talk about programming in B. So B is a formal method which was initially designed for correct by construction to create code for safety critical systems. But it has some interesting foundations, namely it's built heavily on sets and logic, and it has tool support, I mean, in the form, for instance, of code generators and provers, but also in form of the ProB tool that we developed at the University of Düsseldorf. And so initially, the B method, has been used quite heavily in the railway industry. I mean, it's far from being as widely used as Python, but within the formal methods area for safety critical systems, it's one of the more successful methods, I would say. It's also been used not just to create software, but also for analyzing systems and for data validation. And that's one thing I want to talk today about, that this formal method can actually be used and extended into something more akin to a programming language. And here I'll try to show some of the more interesting aspects of that. I'll try to show them in this talk using our ProB tool as an execution mechanism. So it's a validation tool and model checker, but at the heart, it has a constraint solver for predicate logic and notably set theory. And in here is, see that the console of the tool running where you can type expressions. And here you see there's a set unification that has been taking place. You can use set comprehensions, set union. Obviously, you have all the set operators, and you can write expressions and predicates in that language. You can have nested sets of sets, arbitrarily nested. And the tool has built-in support for constraint solving, like here, finding the square root of a number or finding all square roots, and so on. Oh, sorry. Okay, yeah. And so what are the logical foundations? Maybe very briefly, I don't have time, and this would merit another talk. And for those familiar with Prolog, I mean, the one difference would be that it's strongly typed. Also, the set theory is strongly typed, so which has, as a bonus, you don't have all the paradox issues. And you have typing, which obviously, I mean, I find very useful for safety critical systems. Also, it uses classical monotonic negation, so there's no non-monotonic reasoning built in, which is also, I mean, with a background from proof, as a can be seen as a bonus there. And I mean, its syntax is actually quite close to the kind of mathematics you and I write in our papers, like at the bottom here. That's a B expression, and it may look like something you write in your papers. And while it was initially designed for proof and code generation, also in our applications, we have been misusing it as a high-level programming language over the years. And this actually led to some interesting applications. So for data validation, where we check the configuration of, say, complex railway systems and have lots of complicated properties that need to be checked, which are necessary for the safe functioning of the system. And there it turned out that B could be used as a programming language. And I've all tried to answer the question, why was it successful? And I think one reason its foundation in set theory, its ability to talk about sets of objects and have a seamless transition between data and programs, which goes even further than Prolog, I think, where you also have this kind of mix between data and programs. So I'll try and give a very brief demo, given the time constraints of here in the Jupyter notebook. So it's also running Python there in the background, communicating with our Pro-B kernel written in 6's Prolog. And here you see in these cells, you can then write B expressions, which, as you see, look very much like the mathematics you and I would use in a paper. And here I've defined the set of all primes, and I use the set intersection to get the primes up to 100. And here you get the result. So here note that the tool has found out automatically that one of the sets was infinite and has kept it symbolic, and the other has been computed. And what I want to quickly show here is that sets are used all the way through in B. So for instance, arrays, as Maximilian Christianus mentioned in his talk, are also represented as sets of pairs. So here's an array of 4 elements. You see here the internal representation is a set of 4 pairs. And that means that all these set operators are applicable to arrays. Like you can compute the domain of an array to get the interval 1 to 4. Here to get all values of an array using the range operator. And you see here you get the range of an array. You can even compute the intersection of 2 arrays, right here. And what does that give you here? Namely, the positions at which the arrays are identical. Here they are identical at position 1 and 4. If I take the domain of the intersection, I get the indices, 1 and 3, where they coincide. One interesting thing is also functions are also sets of pairs. So just like in mathematics here, I've got the increment by 10 functions of the natural numbers. It's also a set of pairs, an infinite one, but meaning both are sets of pairs, so you can use set operators to combine them. So you can mix data and functions. So here I compute the intersection of an array with an infinite function, and I get then the intersection here. In this case here, okay. And then here I've got another thing is, for instance, the relational composition operator between this function and an array is simply the map function from functional programming. And so that's again another use of a set operator, which can be applied to compute the map over an array. Okay, let me go back. I'm running out of time. But I mean, I think the conclusion here is that it is possible to program in set theory and logic in B. And I think with that, also with there are various other related similar formalisms where this could also be true, like TLA plus alloy have a very similar foundation. And I mean, I think it's something we aim for in the longer run, that maybe through that we can get a formalism of programming languages that is very close to mathematics. So one big question is, I mean, can we achieve performance similar to regular programming languages? So ideally, if you were to write a pure function, it should be executed as quickly as in Haskell. If you write a pure constraint program, it should run as quickly as in 6's Prolog, and so on. And so that is our long-term goal. Okay, so thank you.
Great. Thank you so much, Mihail.